I now want to consider cases where there is internal heat generation. While this may not be a particularly common problem, in some cases it can be important. For example, if you have radiogenic heating or if you have electrical heating in a system. So I'm actually going to do this in the context of radiogenic heating, in that I'm going to look at a specific example of the vitrification of high-level nuclear waste, which relates to the area that I research in. Now, high-level nuclear waste arises from the reprocessing of spent nuclear fuel to extract the reusable uranium and ingrown plutonium. Reprocessing results in a highly active liquid waste, and that is then immobilized, or can be immobilized, by vitrifying it, i.e. turning it into a glass. This glass is cast into stainless steel cylinders and is currently stored in specialist above ground stores where they are cooled by natural convection. Because the radioactivity in those cylinders means that the temperature can be several hundred degrees centigrade within the cylinder due to the radiogenic decay. Specifically, the temperature will be high for the first 300 years due to this internal radiogenic heating, because there are two particular beta emitters, namely cesium-137 and strontium-90, both of which have half-lives of approximately 30 years, and essentially it takes 10 half-lives to get things to a level where you no longer need to consider them to the same extent, and certainly in terms of their impact on temperature. After 300 years, they will have relatively small impact on the temperature of the system. So, what's the specific problem we're looking at? Well, we have a cylinder of glass that has a radius of 0.215 meters if we're looking at what's done in the UK. The glass will have a thermal conductivity of the order of 1.09 watts per meter per Kelvin, and I've given a particular value of the heat generation per unit volume of 16.7 kilowatts per meter cubed. And if the surface temperature of the glass is 200 centigrade, what would then be the temperature on the center line of the glass? Well, to tackle this problem, we're going to assume that the radionuclides are uniformly distributed within the glass. That means we can assume that the heat generation, Q dot, has a constant value throughout the volume of the glass. We're also, because we're dealing with a cylinder, going to use cylindrical polar coordinates, and for simplicity I'm going to assume that the cylinder is very long, so that the temperature distribution can be taken as depending on the radius only. I'm also, and this may seem a little bit odd, going to assume that the temperature distribution does not vary with time. Strictly it does vary with time. We know after 300 years it will not be the same as it is now, but because that time variation is slow, it's reasonable to ignore any change with time in the calculations that I'm going to do. Now, so far we've met the one-dimensional heat conduction equation in its full version in Cartesian coordinates. I've shown it here just by way of reminder. The left-hand term relates to changes in the stored energy in the system. Q dot is the energy generated per unit volume, and then this is looking at the variation of temperature with position. If we transform to cylindrical polars, then we get an equation that looks similar but not identical. Again, the left hand side relates to the energy stored in the system. The Q dot is the energy generated per unit volume, and the differential term now has the form 1 over r partial d by partial dr of kr partial dt by partial dr. Now, as I've said, I'm going to treat this as a steady state problem. The dt by dt term will be 0, and the partial differentials with respect to r become complete differentials, so I can rewrite this equation as 1 over r d by dr, r dt by dr equals minus q dot over k. I've also implicitly assumed here that k is not a function of position or temperature. This equation I can integrate once straightforwardly, which will give me r dt by dr on the left hand side equals minus q dot over k times the integral of r dr on the right hand side, giving me overall minus q dot r squared over 2k plus some constant of integration on the right hand side. If I rearrange that equation and then integrate once again, I'll go through the following process. I'll first of all get dt by dr equals minus q dot r over 2k plus c1 over r. Now I do my integration with respect to temperature on the left hand side, with respect to radius on the right hand side. Left hand side just integrates to t. The right hand side will give me q dot r squared over 4k plus c1 log of r plus c2, where both c1 and c2 are constants of integration. Now, in this particular case, I have a cylinder. We would expect everything to be symmetric, and obviously also a solid cylinder has a value of r that equals 0. Log of 0 is a problematic function, and to avoid problems at r equals 0, we would therefore say that the constant c1 must be equal to 0. And the other thing I'm going to say is that at r equals r0, where this is the outer radius of the cylinder, T equals Ts, the surface temperature, and on that basis I can evaluate my second constant of integration to be equal to Ts plus Q dot times R0 squared divided by 4K. For putting this all together, the temperature in the cylinder equals the surface temperature plus Q dot over 4K, R0 squared minus R squared, or this is more commonly written in this form here, where that second term is expressed as Q dot R0 squared over 4K times 1 minus R squared over R0 squared. And that temperature distribution is obviously parabolic in form, as shown in the adjacent graph. We can also rewrite this temperature distribution in a normalized form, whereby I can simply say that temperature at any point in the cylinder minus the surface temperature divided by the center temperature minus the surface temperature is equal to R over R0 all squared. It's also, of course, possible to work out the heat flux by simply using the standard Fourier's law, again in cylindrical polar form, and applying that to the overall temperature distribution gives me that the heat flux is Q dot times R divided by 2. Going back to the actual temperature distribution, I originally asked what is the surface temperature based on the values that I've given, the heat generation per unit volume, the size of the cylinder, etc. That would mean that my center line temperature was 377 degrees centigrade. Now, it is actually then possible to link this model with other models to obtain further information. So, for example, if I wanted to know the temperature of the stainless steel canister, or more exactly the outer surface temperature of the stainless steel canister around the glass, we know how much heat is being generated per unit volume, hence we can calculate the heat flow out of the glass, as shown here, which gives me 2.425 times 10 to the 3 watts per meter. And if I plug that into the one-dimensional cylindrical resistance model applied only to the stainless steel cylinder, then I can work out what the temperature drop across the cylinder is, assuming that the inside surface of the cylinder is at the same temperature as the glass, which implies that there is good thermal contact. That's probably reasonable because the cylinder is likely to shrink onto the glass. You can see in this case that there is a very small temperature drop, which is not surprising, thermal conductivity of metals being much higher than that of the glass and the cylinder only being thin. But by combining those two models, I can now get a description of the temperature in my vitrified nuclear waste and the stainless steel canister, granted that I've made some simplifying assumptions, such as the fact that the cylinder is effectively extremely long. This is not true in practice, and you would expect some variation from the top to the bottom of the cylinder as a result. Also, the casting is unlikely to be absolutely perfect, which would further complicate the detailed temperature distribution. Now, that was specifically the case for cylindrical geometry. you can actually undergo the same general analysis for a one-dimensional planar wall with steady-state heat generation. For completeness, I've given those equations here. Here is the one-dimensional equation in Cartesians. I've said that I'm basically dealing with a steady-state situation again, which simplifies the equation to d2t by dx squared equals minus q dot over k. Integrate once, I get dt by dx equals minus q dot x over k plus one constant of integration. Integrate again, and I get t equals minus q dot times x squared over 2k plus c1x plus c2, where c1 and c2 are both constants of integration. If the system is symmetric and has a total wall thickness of 2L with a surface wall temperature of Ts, then this will be the temperature that you get from that distribution when you work out the values of C1 and C2. Of course, it does not have to be symmetric, and in which case you would get different results for the values of C1 and C2, and thus for the detailed temperature distribution. So to summarize what I've covered here, having initially gone through the solution to the problem I left you with last time related to the casting of cast iron in a sand mold, I've then gone through how we can incorporate heat generation into steady state problems, specifically in the context of vitrified high level nuclear waste canisters, and then briefly just shown you how you get the similar equations for the one-dimensional planar case. Thank you.